Hello folks, in this video we are asking a simple question. If we have a mixture of gases, let's say monatomic, diatomic and polyatomic or whatever in a container, can we still use the equation PV is equal to nRT? That is, for pressure we take the total pressure of the mixture, the total volume of the container, N as the total number of moles, and T of course is the common temperature of the mixture. Do these variables satisfy PV is equal to nRT? The short answer to this question is yes. And this is an experimental fact. So now let's start by using this to solve a few problems. So the first problem is the following. We have 3 moles of carbon dioxide and 2 moles of oxygen occupying a 2-liter container at 300 Kelvin. What's the pressure? Let's go ahead and directly write down the pressure is P, the total volume is 2 liters, so 2 multiplied by 10 power minus 3 cubic meters, we are using SI units, PV is equal to N, so 3 moles of carbon dioxide and 2 moles of oxygen, so that's a total of 5 moles, N, R is 8.3 joules per Kelvin per mole, that is again the SI units, nRT, the temperature is 300 Kelvin. So solve for the pressure and that gives us 62.3 times 10 power 5 pascals. Let's go to the next problem. In this problem, we have 4 moles of hydrogen and 2 moles of oxygen are burned in a 22.4 liter container. The reaction goes to completion. So the reaction that we are looking at is hydrogen burning in the presence of oxygen, 2H2 plus O2 goes to 2H2O. So that is 2 moles of hydrogen and 1 mole of oxygen will give you 2 moles of water vapor. Why water vapor? Because at 800 Kelvin, water is in the form of a gas. Now we have 4 moles of hydrogen and we have 2 moles of oxygen. So therefore that should give us 4 moles of H2O. Correct? So we end up with 4 moles of water gas, that is steam. So PV is equal to nRT, P times V, V is 22.4 liters, that becomes multiplied by 10 power minus 3 cubic meters. PV is equal to N, R is 8.3 and temperature 800. So let's solve for the pressure. That gives us 12 times 10 power 5 pascals. In this problem, we have a container which has a volume of 22.4 liters and it has got hydrogen at 273 Kelvin and the pressure is given as 1.01 atmospheres. Now, 1 atmosphere, let's see what that is. 1 atmosphere is going to be about 1.013 times 10 power 5 pascals. And the gas weighs 2 grams. Now 2 grams of hydrogen is 1 mole of hydrogen. So keep that in mind. So 2 grams is 1 mole. That is the number of moles N. What is the degree of dissociation? Let's say a fraction F of the molecules has dissociated. So what does the reaction look like? Dissociation, H2 goes to 2H. So essentially 1 mole of hydrogen will become 2 moles of hydrogen atoms. 1 mole of hydrogen molecules becomes 2 moles of hydrogen atoms when 1 mole dissociates. Now a fraction F of the total 1 mole, so F times 1 is the number of moles that is dissociated. So we start with 1 mole of hydrogen, a fraction F of 1, so that is F moles has dissociated. So this is the number of moles of H2 plus F becomes 2F moles of dissociated hydrogen. So the total amount of gas is 1 plus F moles. This is a mixture of undissociated H2 and dissociated H atoms. So now we simply go ahead and apply PV is equal to nRT. So the pressure is 1.01 times 1.013 times 10 power 5 P times volume 22.4 multiplied by 10 power minus 3 PV is equal to N, which is 1 plus F times R, 8.3, times temperature, 273. So all we have to do is solve for F. And if my arithmetic is correct, F turns out to be about 0.0114. That is the fraction of molecules that has dissociated. And here is our last problem for this video. This is again one where a fraction F of nitrogen dissociates. So in other words, N2 goes to 2N. So once again, if 1 mole of N2 dissociates, it becomes 2 moles of dissociated N atoms. So before dissociation, the equation is the pressure is P, volume is V, is equal to N, which is, we are told it's 3 moles, so N, R, temperature 300. And the new pressure P prime, when I raise the temperature to 900 Kelvin, the volume remains the same, is going to be how much? Again, let's say F is the fraction that has dissociated. If a fraction F of the gas dissociates, we start with 3 moles, so 3F is the number of moles of N2 that has dissociated. That has now become 6F moles of dissociated N atoms. So if we start with an N of 3, minus 3F is what is undissociated, plus 6F dissociated F. So the number of moles is from this 3 plus 3F, so 3 times 1 plus F times R times 900. That's the temperature now. So from this, if I divide the second equation, P prime by P, by the first equation, V cancels, 3 cancels, R cancels, 900 by 300 is 3 times, I am left with 1 plus F. So the final answer, what is the new pressure? The new pressure is the old pressure multiplied by 3 times 1 plus fraction of dissociation. That's your answer. That's it as far as the problems are concerned. Now I told you that we can go ahead and use PV is equal to nRT for a mixture, and I showed you how to use it. But can we justify it? Now some people will say, look, supposing this volume is occupied by just N1 moles of gas 1, then the pressure P1 exerted by that gas will satisfy P1V is equal to N1RT. Now if I replace this gas by N2 moles of the second gas, that will exert a pressure P2, and that will satisfy P2V is equal to N2RT. And if I replace it by the third gas, that's going to satisfy P3V is equal to N3RT. Now people will say, why don't we just add the 3 equations? We will get the total pressure defined as P1 plus P2 plus P3 should satisfy P times V, V is common, is equal to N1 plus N2 plus N3, total number of moles N, where N is N1 plus N2 plus N3, times RT is common. So you see, this is the proof. Some people will claim that we can go ahead and use this equation for a mixture. But hold on for a second, this is not a proof. Why? Because this equation holds when only this gas is present. This equation holds only when this gas is present. This equation holds only when this gas is present. When all 3 are present as a mixture, there is no guarantee that these 3 equations are valid anymore. So we have to reach to experiment. And Dalton did the experiment, and experimentally he showed us that the resulting P, which satisfies this equation, is given by P1 plus P2 plus P3, which are called the partial pressures of the 3 gases. So we have to take this result that we can simply use this equation for a mixture as an experimental fact. That's it for today, folks. See you in the next video. Bye-bye.